I'm not gonna do it. But I mean, and so you more graduation, so like you know, we really need to do breakfast. You got to be with the day group, and you got to do the redheaded chick.
Oh, gotcha.
One of you can be Amelia, the other has to be the kid. Because you got to be shot.
Well, good evening, everybody. It's finals week. Yay. Thank you for coming out. Those of you presenting, definitely, and guests in the room, thank you very much. You know, we've got Chancellor Allison with us, and we have Deb Marr, who's the director of the Sustainability Studies program.
And as well. Yeah, Professor Brigowski and our director, Michael Sanders, from the Purdue Polytechnic.
Yes, so two campuses coming together for these projects. For my part, we've got our sustainability practicum course. So this is actually a combined course with our undergraduate and graduate students. It's been the first half of the semester, going to our lecture series, part of that, but also learning about leadership and putting sustainability into practice and how to be that leader. And then we spent the second half of the semester working with students from Purdue Polytechnic to address a sustainability challenge on campus, and we have a community-based project as well. And hopefully Jameson Zarnicki will be with us shortly from the Elkhart Environmental Center, who we're doing a project with as well. So really sort of a nebulous problem in terms of sustainability that students were all tasked with addressing. If this was something that could be addressed, should we do something about it? If so, how? Coming up with best practices and sharing a good return on investment for those. So a couple of them take place, are proposed concepts, I should say, for the Sustainability Showcase area, the 10 city lots just west of the Schurz Library. So looking at things we can put in there. So these are the two you'll be hearing about tonight, were some of the top selections based on the feedback we got from campus and community partners, what they wanted to see and do an interactive space and what they wanted to learn about. So we asked the students to vet some of these projects to see what we could do with them. And then we had a project with the Elkhart Environmental Center where the director reached out to me and said, you know, I'm trying to do this thing, can you help out at all? So we said, well, maybe. So we looked at a project there as well. But it's been a fun, I think, bringing together of the two classes. And I will let Sarah say a little bit about what their class is doing.
Okay, so the mechanical engineering technology students were in the mechanical design class. They spent the first part of their semester sort of practicing and iterating through how to manage a design project from the problem through selecting alternatives and doing some background to do some detail work on your chosen solution for the problem. So about mid-semester then, we got together with the IU class so that they could do a project in conjunction with them, following those same sort of steps of the design process, iterate, do some detail work, and create some hopefully reasonable approximations for the feasibility in terms of the technical details for these projects. So that's where they sort of fit together.
But for the most part, we'll let them tell you about the projects. But before we get started, they're each about 20-minute long presentations. They definitely want questions because they've got answers and in-depth insight on what they've been doing. I do want to invite you to, if you have not yet helped yourself to a beverage, it's warm in here. We've got some refreshments in the back of the room, so please get up whenever you would like. That means everybody. Help yourself to some refreshments. And I'm just going to hang out in the back because we practiced in this room and everyone knows what we're doing with the technology, right? So just chill and enjoy the presentations. So with that said, I'm going to pass it off to the first group.
Straight. You gotta push straight. This thing's over. You fix it, I'll introduce it. Good. Is it working? Maybe it's not all, I want that. No.
Is it on?
We'll go old school. It's cool. We will adapt. We'll adapt. Hi. Hi. Welcome up, Purdue. We start out by introducing ourselves. I'm Sam Elliott, sustainability manager.
I'm Leah McDonald, sustainability minor. I'm Bailey Shea, sustainability major.
Brandon Gruber, mechanical engineering technology. I'm Anthony Rulli, also mechanical engineering technology.
Okay, well, to start out, we want to start the video just to sort of set up our overall theme, what we're doing. Brandon? How you guys? You guys want to get a pop? Get a pop? Answer?
It's just sparkling water.
There you go. This is like you want. That's okay. You know what? The video, it was about what we're facing globally as far as global warming, but that's okay. You know what? I got no. So we will go with that. So anyway, with sustainability, we're always taught to look at the bigger picture and then start to diagnose it down into something more manageable and then go from there. And so for us, we started out with the bigger picture of global warming. And so some of the facts about just water consumption on our planet in general that we considered in order to conceptualize what you'll see as the project goes on, was what water is used for in general. So 70% of the water globally is used for irrigation, which is obviously the majority of it. And with global warming increasing, which is expected to rise, if I remember correctly, it's expected to rise 20% over the next 25 years in regards to just evaporation levels. And what you think is like, you think, all right, global warming, the obvious, the ice caps melting. But what we were concerned about was with global warming, evaporation rates increase dramatically. And what you see with that is you have increased rainfall that happens drastically. So you have quick successions of rainfall instead of sustained seasons like we used to see. You also have a lot more dry and arid places where we're just not hitting rainfall. And so you think, we have these rapid successions of water that come down. So that, contributes to the overall water table. But the problem is, with the way our planet is set up, is the vast majority of it drains into the ocean, which is natural, and that makes it not viable. So that was sort of the global issue. And then, so, like I said, sustainability, we have to break it down a little first. So we looked at it locally. And locally, we're actually, in Indiana and South Bend specifically, we sit pretty well. We're about the average, we're a little bit below average as far as annual precipitation, but which is, it ranges about 39 inches annually. But that does allow us, to this resource that we can use. So for us, we were asked to conceptualize a water catching system that could be used in our green space. Go ahead, you guys can get it. It could be used in our green space here on campus, and we'll explore some of the details later. So the function for us would be to use this, this problem of global warming. We see this rainfall, and we've all seen, it was a couple months ago, we had the massive flooding. And I'm sure you can remember summers past where you got next to absolutely no rainfall. And so we wanted to try to maximize the rainfall we are getting. And again, we conceptualized water catchers, and Leah will tell you a little bit more. She takes a little further.
So when we were thinking about design concepts and the intervention of sustainability with this rainwater catchment system, we had some criteria that we had to keep in mind. The first thing was the space allotted. So how much space we had available for each single unit, and how many we would be able to implement in the sustainability showcase area provided, as well as how much ground or garden space the units could possibly cover or shade. The next criteria was cost, which is mostly about material, and that will be actually discussed in a little bit more detail later. The third criteria was purpose, which we decided was to enhance our environment to an innovative and sustainable water catchment design and function. And the fourth criteria was functionality versus aesthetics. So does it look good? Does it run well? Can both of these components be combined effectively? And the last criteria we looked at were overall benefits. What will a rainwater catchment system do to help our campus and its surrounding environment? So for concepts considered, we wanted to look at what was already in existence. So first we looked at the roof runoff system, which is the popular concept for households. There are four main components of the roof runoff system. The first one is the catchment surface, which roofs are used to harness a directed flow into tanks. For domestic and high quality irrigation use, metal roofs are actually the best. They shed the most water and are the most inert of all roofs. Second is the guttering system. This picks up the flow from the roof and directs it towards the catchment container. The third is the catchment guard. This feature collects all of the bigger items that may have collected on the roof, like leaves, that you want to avoid flowing into the tank. This feature also helps ensure good water quality and reduces the maintenance of the tank. And then last is the catchment container, which is a cistern or a tank that is below ground and is used in cold situations where the tank would freeze if it were left above ground. They can also be simple rain barrels, which hold a significantly less amount of water and can be used in areas that incur hard freezes in seasons where this risk is no longer present. Tanks can be made of plastic, concrete, wood, and all have their embedded energy and environmental repercussions. Next was the industrial model. So large-scale rainwater collection systems provide great economic and environmental benefits because of their overall size and ability to mitigate both stormwater runoff and municipal water usage. However, they also demand greater attention to hydrology concepts, system design, competent installation, and properly designed system components. They're very similar to the roof runoff systems in that the rainwater captured is in the same way, just on a larger scale. So rainwater is channeled from the roof of the most suitable business buildings into storage tanks, passing an integrated filter to remove large debris, etc. And finally was the biomimicry model. And the overall idea is just capturing rainwater similarly to the other methods mentioned to use for mostly gardens and surrounding areas. The design is not only based on the beauty of greenery, but also on the benefits of being able to keep the greenery healthy and hydrated through the system. So water will collect on the leaves on the top of the design, then trickle down into the water column where it can be stored as a single unit or as part of a larger sectional unit. And an inlet column will prevent disturbance of fine sediments on the base of the unit.
So the biggest thing with rain catchers in general is you need a lot of surface area to make them viable and efficient. So that's why a lot of times, like you saw on the last slide, they utilize the rooftop of the building because it gives you the most surface area compared to these standalone systems. But the main focus for this project was a standalone water catchment system. So we couldn't really utilize a building rooftop to complete our project. But some of the things we were up with were these two kind of final designs that we decided to go with. Mostly for cost efficiency and just overall size. We didn't want to make them too big, too bulky, and too expensive. So we wanted to keep them small enough that they were still affordable and efficient, but still could utilize the rainwater that we were getting out of them based on kind of our averages that we were seeing there. So you can kind of see the basic sizes there of the two, and that could be adjusted down the road depending on performance of the catchment systems. But they're about just under 3 feet tall, and about 3 feet or so, 3 feet or less wide there. So it gives you a pretty good amount of surface area for the water catchment. But so these were the two, and then the one on the right there was obviously the biomimicry model. Not an artist, but we were able to kind of design something that would somewhat resemble plant and leaves that plants use to do their own catching of water. So those are the two main models we came up with. And some materials we looked at stainless steel and aluminum. We also looked at doing something out of limestone, but the aluminum kind of just proved to be the best all-around material. It's very lightweight, obviously, and the stainless was just too expensive to make this type of setup viable. So we ended up going with the aluminum, and you get the pretty similar resistance to weathering and the outdoors with the aluminum, close to what the stainless steel will give you. And then for the drainage system that would connect the catchment systems together, you could do kind of a daisy chain setup to attach them all together. We would use PVC piping for that. Obviously, it's just very inexpensive, and it works well underground, and we could use that to kind of run the drip lines off of the units, off of the catchment systems. And those catchment systems would have kind of like a nozzle to stop the water from flowing when you have no rainfall, if you wanted to conserve the water for times where you're not having any rainfall, and then utilize it then. That would kind of give you the best performance out of them.
So, like Brendan mentioned a minute ago, we wanted to go with aluminum for the water catchment system, and we arrived at that based off the software that we have access through. We have access to through Purdue's library. It's you can set up so you put in your parameters and then the conditions it's going to be in, and it'll give you a kind of a cost analysis of where different materials fall. So you can see where it's circled in blue up there is where aluminum sits, and it's a scale from kind of a rural environment to perfect situations where you're not going to be experiencing weather or any other kind of weather corrosion. And that's how we arrived at using aluminum. And then we have a kind of a cost breakdown just in materials, what it would take to build one of these. This doesn't include labor because labor would kind of change depending on who's building it and then how many of them we're building. So can this be done and can we install it? We can. We have the green space as you saw a couple slides before with the chart. And then flexibility and cost adjustment, we can move them throughout the green space however we need them. And then depending on how many we make, we could get the price down. If you make a lot, people will generally cut you a deal in terms of manufacturing as opposed to using like one or two.
So will this help us move where we want to go? We think so. So number one, our cost reduction is going to be down. It's going to be a lot cheaper than installing traditional watering systems like sprinkler systems into the ground. It's also, we'll see a return on our investment eventually. Also, it's going to be better for the community and for our campus maintenance. They have a lot more access to these watering systems. Finally, it's going to help improve our campus aesthetic. Right now, we really don't have a lot of pretty things on campus. So it's going to make us look like we care about our campus more, which is something we want to take pride in. Also, we're using biomimicry for our design, so we're going to be able to mimic nature more, and it's going to be more pleasing to the eye. And finally, these are some alternative options for what you could do at home. So the first one is something you can do with your kids. It's just a 2-liter bottle that you just cut in half, and it's obviously not going to get that much water, but it's a way to teach children more about sustainable living at a young age.
The second one is based off of a roof catching system. So it's obviously going to catch and hold a lot more than this 2 liter. Yeah, so it'll be easier to do water there. And finally, it's just an example of how pretty rain catchers can be. It doesn't need to be a big old box. It can actually look like something that you would want in your yard.
Thank you, guys. Questions? Anybody?
I was interested in the biochemistry to study different plants that capture water and start to look at what was efficient, or was this just kind of a preliminary?
It was mostly a preliminary idea. We didn't really delve too much into actual plant life. That we kind of more so wanted it to be aesthetically looking, more so than actual functionality. But that could always be.
Yeah, I mean, as like sustainability students, we've done sections on biomimicry specifically, and there really is a plethora of different options you could go, but obviously I don't know CAD well, so we were working with what we thought would blend in well with the campus, but there's a whole science to biomimicry. It's pretty interesting. A lot of directions you can go with that. Yeah, go ahead.
Did you guys, or how would you determine how much water you actually collect?
So we kind of looked at just rough volumes of the models themselves, not so much a continuous capture rate, so to speak. The industrial model with the top basin there completely filled was roughly like 24 gallons, and then with the model on the right there, obviously you can't utilize the upper capturing system of it, so just the basin itself was like 2.4 gallons that it would hold, just the rough volume. But we didn't really look into continuous capture rates.
They're kind of hard to figure out with all. We can have general ideas based on statistical rainfall, but that's about what our maximum would be. But yes.
Did you read about any places that are doing this, that are using water catchments, either other universities, campuses, or businesses?
I didn't run across any other campuses. I'm sure there are with sustainability being sort of the up and coming, a lot of cases, but a lot of businesses, especially that are trying to be as sustainable as possible with LEED and everything, a lot of them are incorporating what you saw. This is obviously a little bit industrial for way too, but a lot of places that do require like 1,000-gallon tanks are going over to this and are finding out that with like a good rainfall, you can fill them up and then they can be used. They can last, for months. So it's actually an incredibly efficient system. I think large tanks like this will be the future of, especially, I wouldn't say like necessarily grander scale farming, but maybe more localized farming, like 100-acre farming, that kind of thing. So I definitely think it's the future as far as sustainable farming goes.
So last summer I actually worked for my town, and part of my job was like watering flowers and everything. So we actually did have like a rain catching system, and like we weren't able to use it like every day or anything, but when there was heavy rainfall, we would pull from there first before we use our town water source. So yeah, that's something.
Did you come across any communities who say like Arizona, there's no water, that people can actually sell water back to somebody else that they've been collecting?
So from what I saw, I actually studied this area in Africa that used the design of I guess biomimicry in the sense of like spider webs, how they collect water. Obviously, because they don't get as much rainfall as we do over here. And it was really interesting. I think they actually won an award for their design. As far as the selling